Thank you guys for your time. And I'm a final year PhD student with Professor Katak. And I would be discussing some of the key findings from my dissertation today. So I'll be briefly discussing in the best interest of time. So the topic, as Professor discussed, of my dissertation is to investigate the role of human factors driving instability and roadway environment in safety critical event using the safe system approach. So as you can see, there are a significant number of roadway fatalities and injuries every year, and most of them the crashes occur due to the human factors. Like in 93% of the roadway crashes, human factors are identified to be the contributing factors. So coming to the safe system approach and new data, so we nowadays we have the naturalistic driving study data, which provides newer information about the pre-crash driving behavior, which could not be available in the police crash reports or could be subjective. And the other good thing about the NDS is that besides the crashes, it includes data about the near crashes and baselines. Which could specifically the baseline could be used as a surrogate to the exposure to quantify the risk of the crash and near crash. So basically, we wanted to classify the driving errors and violation in naturalistic driving environment. You can see some of the pictures here, which could be relevant to those captured through the NDS video cameras and equipments. So coming to the safe system approach, safe system approach is basically it provides the multiple protective layers to enhance the safety by tolerating the human mistakes like which the driver makes. And the safety could be improved through safe road users, safe vehicles, safe roadways, and environment and safer speed. So we have been looking at it each of the these elements in various chapters of my dissertation, which I would be discussing. So these are some of the research topics which each chapter would be discussing. We would be discussing how we develop the taxonomy for the naturalistic driving errors and violations, and then capture their investigate their variation across the diverse roadway environments. We would be then exploring the role of these driving errors, violations, distraction duration, and as well as the role of driving instability in these safety critical events in diverse roadway environments. We will also be discussing how we can predict the safety critical events based on the human factors using machine learning methods. And then finally, we also wanted to see how these human factors relate to pedestrian injuries given a crash, for which we would be using the enhanced police crash reported data. So coming to the first chapter, so the key findings from this chapter have been published in the Journal of Accident Analysis and Prevention, as well as we presented them in the TRB. So basically, the goal of this chapter was to develop a systematic framework to classify the driving errors and violations, and then to see that how these driving errors and violations vary across different environmental contexts. So we have a sample from the NDS, which includes crashes, near crashes, and baseline. Based on the key results, we found that human factors still contribute to 93% of the crashes, where the recognition and decision error have the highest share in these crashes. We also looked how these errors are distributed among various roadway environments, and we found that recognition error are predominant in school zones, business and industrial location, and urban areas. So basically, the taxonomy which we developed, that was based on the theoretical perception reaction process. And previous study have also used, similar concepts and different themes to classify the driving errors and violations. But as we discussed earlier, they were based on the police crash reports, which could be subjective and which may not capture the pre-crash driving behavior. However, as you can see in the table below, that our findings were more or less similar where we found that still the recognition and decision error play a very critical role in the crashes, contributing to a significant amount of crashes. So this is the taxonomy. This is the visualization of the taxonomy, which we have developed. So using the perception reaction time, we classified the driving behavior into recognition error, decision error, performance errors, and violations. While there could be some other errors which could not be directly related to the perception reaction time, like physical condition errors and experience errors, so we put them in a separate category. However, not that, I mean, these errors can influence the ability of the driver in any phase of the perception reaction process. So coming to the crash risk at the very basic level, we wanted to see, I mean, to compute the crash risk associated with each driving errors and violation, as well as diverse roadway environment. So you can see, I mean, the recognition error has the highest crash risk, followed by the performance error, and then the experience or exposure error. Similarly, I mean, in school zones, business industrial location, or urban areas, the crash risk is higher. You can see the Venn diagram, which shows the contribution of the key factors, which include human, roadway, environmental, and vehicle factors. So coming to the second chapter, this has also been published in AAP, and we have presented the key findings from this chapter at TRD. So basically in this chapter, what we were doing, this was based on the hypothesis that the diverse roadway environment may encourage or discourage a specific type of errors, which may also influence the safety critical events. So what was the purpose of this study was that, like, we hypothesized that certain roadway environmental environments may not induce crash risk or near crash risk directly, but indirectly as well. So to capture the overall effects of a specific roadway environment, we wanted to conduct the path analysis to see where there could be some significant indirect correlation of these roadway environment with the safety critical events. So as you can see, this was the first model where the response outcome was our variable was different types of error. We applied multinomial logic model here, and as you can see that the chance of recognition and decision error is higher in school zones, business industrial location, and urban areas. So similarly, for the event outcome, which include baseline, near crashes and crashes, we developed various models, which includes like the simple ordered probability model, as well as we looked for the proportional odds assumption. And then there we found that some of the variables, they violate this assumption. So we relaxed that by developing the partially proportional odds model, because I mean, if some of one or more of the variables, they violate the assumption, and we do not account for that in the methodology, so the result could be inaccurate. So we found that based on the AIC and BIC, the partially proportional odds model were performing better, and we came to know that all the driving errors and violation compared to no driving error, they are positively related with the crashes and near crashes, which means that once a driver is involved in crash, in recognition error, for example, or decision or any other type of error, the chance of involving in a crash or near crash is higher. So these are the pathways, and these are the illustration of the key results from the path analysis which we conducted in this chapter. And as you can see, like, I mean, compared to the interstate, for example, the moderate residential, school zone, and business industrial area, they induce certain errors, like they increase the chance of recognition error, decision error, which also, I mean, contribute some crash risk. So besides the direct pathways of these roadway environment, there are indirect effects which should be captured to understand the overall effects of the specific roadway environment on the crashes. Coming to the third chapter, in this one, this was based on a hypothesis that a driver, after making a specific errors or violation, may become and realizing it, the driver may take some corrective actions which may make him or her more volatile, while the volatility in turn could be related to the safety critical event. So basically, we were looking at these pathways, but from the methodological standpoint, we thought that there could be some unobserved factors associated with the driving instability, which is coefficient of variation of speed, as well as the safety critical events. And there could be some correlation which needs to be captured in the methodology. So coming to the results obtained through the giant estimation, so we noticed that there is a significant correlation between the unobserved factors, which are significantly associated with the coefficient of variation of speed, as well as the event outcomes, as well as you can see that all the driving errors, they increase the driving instability. In simple words, driver who make errors and violations, they become more unstable, as well as the driving instability is positively correlated to the crashes and near crashes. So again, you can see, I mean, that, okay, the driving errors specifically and violation that not only impose or induce the crash risk or the near crash risk directly, but they also have some addition to this crash risk when the effect of these errors and violations on crashes and near crashes through driving instability are taken into account. Again, we were interested that, okay, I mean, a driver could be distracted, but the duration of distraction could have also influence on the driving instability, as well as the near crashes and crashes. So we conducted the path analysis through giant estimation, but we accounted for the nonlinearity in the effects of the distraction duration. That was, we included a spare term of secondary task duration, and we found statistical evidence that there is some nonlinearity. So when we computed and plotted the direct and indirect effects, so two things we noticed. One was that the effect of the distraction duration on both coefficient of variation of speed as well as safety critical event is nonlinear. And the other thing was that if we conduct the path analysis, so I mean, we found significant indirect effects of distraction duration on safety critical events through driving instability. So to conclude, the total effect would be higher than the direct effect of distraction duration on crashes. These are some potential countermeasures, how we could mitigate the chance of crashes which occur due to the distraction duration. So some of them include like providing and improving the message and signs, using the hands-free devices instead of cell phone, like for texting, but when needed. Otherwise, the use should be avoided. And then we could have multiple driving assistance systems, which could also reduce the instability and ultimately the crash and near crash risk. Coming to the fifth chapter, so in this chapter, what we were looking at how the human factors relate to the pedestrian injury, and we applied the finite mixture model. So the key goal of the key purpose of applying this finite mixture model was that we hypothesized that, okay, there could be some unobserved factors based on which the pedestrian could be divided into unobserved classes, and the effects of the observed factors could vary across these unobserved classes. So first of all, we developed the taxonomy for the pedestrian behavior, pre-crash pedestrian behavior, as well as the driver behavior. So as you can see, I have taken these pictures from the North Carolina PBCAT tool, which is actually a database for pedestrian and vehicle crashes. And the good thing is that although this data is based on the police crash report, but they have like further investigated the forms and extracted some more detailed information about the pre-crash driving behavior, which could be not available directly in the police crash report. So we found that human factors contribute to 60% of the pedestrian vehicle crashes. So in this study, we developed the simple order probit model, which we call the base model. And then we applied the finite mixture model. So as you can see, we got different coefficients or parameter estimates for different classes. So as you can see, for the lightning condition, like for the first class, if there is no light present, or if the crash occur in dark time, the probability of being killed in that crash is lower. But in the second class is higher. So this justify or somehow reinforces our presumption that, okay, maybe there could be a higher conspicuity of the pedestrian in the class 1 compared to the class 2, which we don't know and we do not have the data. So as you can see in the lower table that for the class 1, which we call they are safer, so the probability of fatality and suspected serious injury is lower, significantly lower compared to their corresponding probabilities in class 2. So these are some of the potential countermeasures, how to reduce the pedestrian vehicle crashes or the injuries, serious injuries to pedestrian in these crashes. So pedestrians should avoid using cell phone for texting, especially, and they can use the hands-free devices instead of cell phone for emergency calls or when they are too much important. Similarly, pedestrian identification and automated braking system could help in reducing violations. May not reduce the violation, but they could overcome the consequences of those violations, or they could help in reducing them. So, and similarly, the driving assistance system could help. So, in the first 3 chapters, when we were investigating the human role in the naturalistic driving crashes, so we were looking at various human factors separately. And then we wanted to, how we can develop, a model where we can investigate the factors of driving errors violations, driving instability and distraction direction, and how we can predict, because all those models were statistical models. So they are good in providing and generating the inferential knowledge, but when it comes to the prediction, so they show a bit weaker performance. But the availability of the new techniques like machine learning methods like k-nearest neighbors, naive-based classification, and gradient boosting, so they provide an opportunity, to have higher out of sample prediction accuracy. And we have quite a bit of human factors, related variables like driving instability, errors, which we want to explore how they could be used in predicting. So this is naive-based classifier, and we use the objective functional model to identify the optimal kernel width, which is found to be 0.11. So we fitted the final model with this value because it has the lowest loss. And similarly, for the KNN classifier, we use different distance as well as the number of the nearest neighbors. So we found that based on the Mahalanobis distance, there when 3 nearest neighbor are used, so the loss would be the lowest. So we selected that. Similarly, for the gradient boosting, we considered the interaction depth, shrinkage, and number of trees in this classification, and we first identified the optimal values and then fitted this model. So as you can see, after accessing the out of sample prediction, we found that the gradient boosting tree has the highest accuracy of 91%, which means that it can correctly classify 91% of the observation in the test sample. Similarly, it worked well for the safety critical events. And based on the most accurate model, we wanted to see the variable importance. And we noticed that the top 5 most important features are human related factors. The top most is the coefficient of variation of speed, and then deacceleration, So it justifies the critical role of these human factors in crashes again. So coming to the conclusion, we develop a systematic taxonomy for the pre-crash driving behavior using the India's data. And then we analyze the new measures of driving instability and safety analysis. We also conducted rigorous path analyses to investigate the pathways from driving errors, roadway environments, distraction duration to the crashes and near crashes. So coming to the potential countermeasures, we can enhance the roadway safety to safe road users by reducing or eliminating errors and violation. How to do that? We can enhance our vehicle to make them more safer by deploying multiple vehicle technologies like powered collision warning system and adaptive cruise control, which could help the driver. Similarly, by providing safe roadway environments or improving the roadways through traditional countermeasures, like we could remove the redundant billboards and which create the visual noise to the driver. And similarly, we could improve the speed of the driver, which we call which we say that okay, the warning system could enhance the stability of the driver and make them less stable. So this was all what I wanted to present. Thank you very much. And if you have questions, so.
Thank you. Questions? You understood everything he said? Everybody understood everything. You want me to ask a question? I have enough time. He is going to defend all this. I'll have enough time to ask him questions.
I have a simple question. Is there any way to categorize different human errors? So how did you do that?
Yeah, so like, I mean, what we did, we considered like, I mean, a thorough research based on the literature, and we tried to see how people have done that. As I discussed that, it was not the first time. People have done that before using different themes, but actually the issue was that they used the, the police crash data. And we made the point that, okay, I mean, they have done it, but those were based on the police crash data. So they may not be, I mean, that could be subjective. So we based our taxonomy based on the perception reaction time, but actually our data was like, I mean, more unique. And yes, we can do that by I mean, applying certain clustering approaches and all, but like this is more theoretical approach. So we have used for the taxonomy. Hopefully.
Okay, so in the interest of time, thank you so much again.
Thank you.
So let's see. Iman joined us from actually Penn State. He started his graduate studies in August of 2017 at Penn State. Before that, he did his master's in Iran from Amir Kabir University in Tehran, and also he's been working on with me on connected and automated vehicles, which is what he will be talking about, and hopefully they will be defending their dissertation soon. So with that, Iman, thank you so much.
Thank you very much.
We look forward to your presentation.
Okay. So all right. Okay. Thank you everyone for attending this seminar. The topic of my dissertation is exploring potential impacts of connected and automated vehicles technologies. Before studying, I would like to thank Dr. Khattak for supervising this study and so many papers that we have published based on the findings of this dissertation. So we know that each year in the United States, we have more than 30,000 traffic fatalities. And this causes billions of dollars to the society. And we know that more than 93% of crashes are due to human error. And Numan talked about human error well. So we are looking for some ways to reduce human error and save lives. Hopefully technology can help us here. So there are so many advanced driving assistance systems today deployed on on-road vehicles and on CAVs. In this study, I'm gonna talk about adaptive cruise control, cooperative adaptive cruise control, pedestrian crash prevention system, and advanced automated collision notification system to see the impact of these technologies in terms of safety and environment, and is there any potential for these technologies to address some of the current transportation-related problems. So there are two research questions that we are going to address. First, how can we quantify the potential safety and environmental impacts of CAV technologies based on testbed data or real-world data? And second, what is the potential for CAV technologies to address some of the existing important transportation-related problems? So this slide shows the framework. So we can see connected and automated vehicles can generate big data. So several sensors that they have GPS data, vehicle kinematics, so on and so forth. By carefully analyzing the big data, we can address the first research question and explore the impacts of these technologies. And if we use conventional safety data sources like crashes, roadway environments, we can look for potential for CAV technologies to address some of the existing problems. In total, in this study, I'm going to talk about 6 chapters. In chapter 1, I'm going to talk about a systematic literature review on CAV impacts in terms of safety. In chapter 2, I'm going to talk about adaptive cruise control and cooperative adaptive cruise control and the safety and environmental impact of these two technologies. And in chapter 3, I'm going to talk about the impact of an AV on the driving behavior of a conventional vehicle. In chapter 4, we're going to see what's the safety impact of pedestrian crash prevention system and will it improve pedestrian safety or not? And in chapters 5 and 6, we are going to see if automated collision notification systems can help us save some pedestrians and bicyclists' lives after a crash. So let's move on to chapter 1. The title is Safety Impacts of Connected and Automated Vehicles, a Systematic Literature Review using Advanced Data Mining and Text Analytic Tools. So I've collected 80 peer-reviewed research papers in which CAV safety impacts have been discussed. Then by analyzing and synthesizing these papers, we extract the most discussed topics. So as you can see, there are 10 important topics that have been discussed in these papers: autonomous emergency braking, cooperative adaptive cruise control, cost and benefit of these technologies, risk assessment, environmental impact, fuel consumption, the impact of different market penetration of CAVs, dynamic intersection or vehicle to infrastructure connectivity, driving tasks, how automated vehicles can affect driving tasks, security of automation, and connected vehicle platoons. So the 4 topics that I put a box are the ones that I'm going to talk about in this study. Chapter 2, the title is Safety, Energy, and Emissions, Impact of Adaptive Cruise Control and Cooperative Adaptive Cruise Control. The findings of this paper have been published in Journal of Transportation Research Record in 2020 and presented at TRB. So the overall goal is to address the first research question to see the impact of ACC and CACC technologies. We have used data collected by United States Department of Transportation in a project named KARMA, in which they have been testing adaptive cruise control and cooperative adaptive cruise control in a test bed in Maryland. So that data set consists of two scenarios. In scenario one, we have 5 vehicles in a vehicle platooning in 2 different modes, ACC and CACC. And in the second scenario, there are 4 vehicles in a platoon, and the last vehicle is trying to join the platoon from a ramp. There are 2 different platooning modes in scenario 2, manual or human-driven vehicles and cooperative adaptive cruise control, or CACC. So what is ACC and what is CACC? Adaptive cruise control, or ACC, is a cruise control system for road vehicles that automatically adjust the vehicle speed to maintain a safe distance from vehicle ahead. So the vehicle has some sensors, a radar, and it can detect the vehicle ahead and adjust the distance and the speed. So it adjusts the speed to keep a safe distance from the vehicle ahead. So if we have, for example, 3 vehicles in a platoon, the second vehicle should detect deceleration and acceleration of the lead vehicle, and then try to decelerate or accelerate. Then after that, the last vehicle, the third vehicle, should detect the second vehicle and adjust its speed with that. So definitely there would be a big latency to first detect and then react. But cooperative adaptive cruise control, CACC, is an extension to the ACC concept. A CACC system adds a wireless vehicle-to-vehicle communication to the ACC system. So the main goal of CACC is to reduce the latency. So in CACC vehicles, in a platoon, we have communication between vehicles. So when the first vehicle, the lead vehicle, starts decelerating or accelerating, at the same time, it transmits a signal to other vehicles in the platoon and tell them, okay, I'm braking or I'm accelerating. And the other vehicles do this at the same time. So the latency would be very low. On the left side, you can see the framework of this study. We are going to use 2 surrogate safety measures, driving volatility and time to collision, to measure safety impacts. And we are going to calculate fuel consumption and emissions to measure environmental impact. Before that, what is driving volatility? You can see 3 speed profiles in this graph, in the blue line, orange line, and the gray line. The average speed for all of them is 10 meters per second. So do you think which one of them has higher volatility? So driving volatility is a surrogate measure of safety that quantifies the deviation of driving behavior from the norm. For example, if you assume a constant speed, the blue line is the norm. So the other 2 lines is a deviation from the norm, right? So driving volatility captures the alterations in longitudinal control of a vehicle. So the more variation, the more alteration you see, the more volatile the behavior would be. So you can see time speed profile, acceleration time profile, and volatility time profile. On the left side, you can see adaptive cruise control. On the right side, you can see cooperative adaptive cruise control. There are 5 vehicles in a platoon, so you can see 5 different colors or 5 different speed profiles. So it's obvious on the right side, if you see the speed profile, the variation of the speed is much lower than, in CACC is much lower than the ACC mode. So we can see following vehicles have smoother speed adjustment when they are connected to each other compared to ACC. And for the acceleration as well. And you can see the volatility over time in CACC mode is much lower than ACC mode. But if you take a look at the speed profile for the CACC in time about 120 seconds, the slope is positive, and the slope of the line, which represents acceleration, is sharper than ACC. Because in ACC, due to some restrictions of the sensor performance and vehicle performance, they can't use a high number of acceleration rates in the algorithm of ACC. But in CACC, due to the technology and due to the connectivity, it's safe to use a high value of acceleration rate. So that's why in CACC, we have sharper acceleration. And sometimes this sharp acceleration increases the volatility. So in general, we can see CACC compared to ACC reduces the driving volatility about 20%. And CACC compared to conventional vehicle, it reduces the driving volatility about 60%. And both of them, CACC improves time to collision, minimum time to collision, about 100%. So CACC can deliver a safer following behavior for vehicles and reduce the rear-end crash risk. And regarding the fuel consumption and emission, you can see CACC reduces fuel consumption and emissions about 4% and about 20% reduction in fuel consumption when we compare CACC with conventional vehicles, and 33% reduction in emissions when we compare CACC with conventional vehicles. So chapter 3, the title is Integration of Automated Vehicles in Mixed Traffic, Evaluating Changes in Performance of Following Human-Driven Vehicles. The findings of this paper, this chapter has been published in the Journal of Accident Analysis and Prevention in 2021 and presented at TRB. So before going to this chapter, I'm going to ask you a question. Suppose you are driving a vehicle in a highway. If you see there is an automated vehicle in front of you, what would be your reaction? Are you going to reduce your speed? Are you going to reduce your distance from the autonomous vehicle? Are you going to lower your distance from autonomous vehicle? So definitely each of you has different behavior when you see an autonomous vehicle. Some of you may trust the autonomous vehicles, some of you may not. So the goal of this study is to address the first research question at a macro level, to see the impact of an autonomous vehicle or automated vehicle on driving behavior of conventional vehicles. We use a data collected by Texas A&M University from a field test bed. That data set consists of 2 vehicles, 5 different speed profiles, 9 drivers, and 2 scenarios, in total 90 tests. So in scenario 1, we have a human-driven vehicle follows another human-driven vehicle. And in scenario 2, we have a human-driven vehicle follows an AV, an automated vehicle. So by using the same measures that we have used in previous chapter, driving volatility and time to collision, we are going to measure safety impacts, and fuel consumption and emission, we are going to measure environmental impacts. So we can see people when follow an automated vehicle, they are willing to reduce their spacing from the autonomous vehicle. So probably people trust AVs. So they lower their spacing and gapping from the automated vehicle. So you can see when a driver follows an AV, it shows about 20% lower speed volatility, about 24% lower acceleration volatility, and about 21% higher minimum time to collision. So it means that when you follow an AV, you show safer behavior. And you will consume less fuel, about 11%, and emit less emissions, about 4%. Let's move to chapter 4. The title is How Effective Are Pedestrian Crash Prevention Systems in Improving Pedestrian Safety? This chapter is submitted at Transportation Research Board in 2022, and it's under review in the Journal of Accident Analysis and Prevention. So the goal is to address the first research question and see the impact of this technology on pedestrian safety. The objective of this chapter is to investigate the effectiveness and reliability rate of the pedestrian crash prevention system, PCP system, utilizing on-road vehicles. So we have used a data set collected by Insurance Institute for Highway Safety, IIHS, in which 92 cars with different size, makes, and models from 2018 to 2021 have been tested and analyzed in terms of safety. So the data have 6 scenarios. In scenarios 1 and 2, a child darts out into the road and there are some parked vehicles obstructing the view of the driving vehicle. And there are 2 different speed profiles, 20 kilometers per hour or 12 miles per hour and 40 kilometers per hour or 25 miles per hour. In scenarios 3 and 4, we have an adult walks across the road and vehicles driving 20 kilometers per hour in scenario 3 and in scenario 4, 40 kilometers per hour. And in scenarios 5 and 6, we can see an adult in the right lane near edge of the road is walking, facing away from the traffic, and the vehicle traveling 40 kilometers per hour in scenario 5 and 60 kilometers per hour in scenario 6. So these are 6 dangerous, situations for pedestrian crossing a road. If you take a look at this 3D graph on the right side, you can see the x-axis represent vehicle model year from 2018 to 2021. Y-axis represent the speed test, 20, 40, and 60 kilometers per hour, and z-axis represent percentage of successful collision avoiding by the pedestrian crash prevention system. For example, for test speed of 60 kilometers per hour, and in 2018, you can see in 20% of hazardous pedestrian crossing situations, PCP systems have avoided collisions, only in 20%. But we can see on average, there is a noticeable improvement in the performance of PCP system technology over time. That 20% has increased to about 49% in 2021. Also, on the left side, you can see the speed at impact for different vehicle model years. You can see the average of speed has been reduced when we go forward in the time, and the accumulation of zeros have increased. So there are more zeros in 2021 compared to 2018. It means that, okay, the system performs better in 2021 compared to 2018. So we developed, we estimated a Hedge sample selection model to see the association of different factors on the performance of the PCP system. As you may know, the Hedge model has 2 stages. The first stage, we call it sample selection stage. So we first identified whether there is a crash with the pedestrian or the vehicle can successfully stop. You can see different variables have significant association with this with the response variable. For example, maximum deceleration, the higher maximum deceleration, the lower the probability of having a collision with a pedestrian. and different scenarios, vehicle model type, and different vehicle body type. So the more smaller the vehicle, compact the vehicle, the better performance of the PCP system. And in the second stage, we estimate the speed at impact, the regression stage. So in general, if I want to recommend you, if you want to buy a vehicle that you want to make sure the PCP system performs well in that vehicle, I would recommend to buy a brand new luxury, compact, low weight vehicle. So find that vehicle. So the model shows that, yeah, 2021, the performance is better than the years before. And the more expensive the car, the better performance of the technology. And the lighter the weight of the vehicle, the better performance of the technology. So buy a brand new luxury, lightweight, compact sedan vehicle. Chapter 5, the title is Understanding the Role of Faster Emergency Medical Service Response in Survival Time of Pedestrians in Fatal Crashes. The findings of this paper is under the second revision in the Journal of Accident Analysis and Prevention. So the overall goal, the overall goal of this study is to address the second research question, to find out the potential for addressing some of the current problems for vulnerable road users. So understanding the role of faster emergency medical service response in survival time of pedestrian in fatal crashes is the objective of this study, and exploring the potential for advanced automated collision notification system to reduce the emergency medical time response time. We have collected about 5,000 pedestrian fatalities from 2015 to 2018 from the fatality analysis reporting system dataset. And by using this framework, you can see there are so many pre-crash factors and a post-crash factor, namely emergency medical service response time. We proposed a model, a geographically and temporally weighted truncated regression with a two-stage residual inclusion treatment model that can first overcome the endogeneity limitation or the endogeneity bias, because the emergency medical service response time and the pedestrian survival time has an endogeneity bias. So you can see increase in the emergency medical service response time, increase the survival time of pedestrian. It doesn't make sense, but the data shows that. And the model can account for unobserved heterogeneity available in the crash data. So this table shows the model. This is a very sophisticated model, but the most important part of this model is the emergency medical service response time variable. You can see the sign of the coefficient is negative, which means that reduce in the emergency medical service response time increases the chance of survivability and survival time. And you can see on the right side, the scatter plot, the x-axis represent the emergency medical service response times in hour, and the y-axis represent the pedestrian time to death in day. You can see the more delay in emergency medical service response, the lower the pedestrian survival time. And also the model can capture the spatial temporal variation of the coefficients. You can see as an example the spatial temporal variation of the coefficient of emergency medical service response time. By addressing this heterogeneity over time and over space, the model outperformed the conventional models. And chapter 6 is similar to chapter 5, but in chapter 6, the title of chapter 6 is Can Faster Crash Notification Time Increase Survival Time of Bicyclists in Fatal Crashes? Application of explainable machine learning using shaft technique. This chapter is the findings of this study have been submitted to the Journal of Safety Research and is under review. So the overall goal is to address the second research question at the system level by understanding the role of faster crash notification time in survival time of bicyclists and exploring the potential for advanced automated collision notification system to reduce crash notification time and reduce emergency medical service response time. In this study, we used about 1,000 bicyclist fatalities from 2015 to 2019 from the FARS dataset. And we developed an XGBoost machine learning model and using SHAP technique to interpret the result and see the associations of the variables. Before that, we need to know the components of emergency medical service response time. So it consists of two parts: crash notification time and emergency medical service transport time. How many minutes do you think on average it takes to report a crash to the police in the United States? It's about on average 3 minutes. So I'll go back to that, but before that, let's see the result of the XGBoost model. So the purple color represents high value of a variable, of a feature. And the yellow color represents low value. So you can see, for example, for crash notification time, most of the purple dots, each dot represents a crash or a pedestrian, a bicyclist fatality. You can see almost all of the purple dots are on the negative sign, the negative side of these graphs. It means that the association is negative. So if you increase the crash notification time, the likelihood of an early death for the bicyclist is higher. But let's take a look at the descriptive statistics of crash notification time. The maximum of the crash notification time is about 241 minutes. It took 241 minutes to report a crash to the police. And the average is 3 minutes. But in some scenarios, in some situations, the average is statistically higher. For example, in late night hours, the average of crash notification time is statistically significantly higher than daylight. And in hit and run crashes, it's higher. And in rural land use, it's higher than urban land use. So how we can address this problem, how we can reduce the crash notification time and save vulnerable road users' life. It is shown that utilizing the advanced automatic collision notification system can deliver crash notification time less than 1 minute, because suppose you have a crash with a pedestrian, your vehicle automatically report the location of the crash to the police in less than 1 minute. And so in some situations, such as late night hours, hit and run crashes, or in rural areas, where no one can see the crash and can report it to the police, your vehicle does it for you. And the overall contribution of this study, you can see this study provides a robust analysis of the impacts of vehicle automation and cooperation technologies using emerging large-scale data obtained from CA field tests in testbeds, and quantify the safety and environmental impacts of these technologies at micro level and system level, and exploring the potential for CAV technologies to address the vulnerable road users' safety problem. So, for example, you can see adaptive cruise control and cooperative adaptive cruise control deliver some safety and environmental benefits both at micro level and system level. And we showed that pedestrian crash prevention system and advanced automated collision notification system can deliver safety benefits at system level. With that, I would like to thank all of you again for attending this, attending and listening to my presentation. And I would be happy if you have any question, please ask.
Questions?